can you see my reasoning here? Can you follow the reasoning? If the green stripe diverges, it doesn't approach any number, then surely the series, which is even higher than that, must also. Alright, so this, alright, are we taping? Okay, this series has a special name, and it's called the Harmonic Series. It was named by Pythagoras. It's been around a while. The Harmonic Series, and I looked it up and tried to understand why he called it the Harmonic Series, but I couldn't understand it. So feel free to indulge in that and enlighten me, especially if you have some music background, but I couldn't understand what he was saying, what they were saying. So I looked up several sites, but it wasn't clear. But anyway, it's a nice name, don't you think? Harmonic Series. Okay. So, again, about the temptation we have, when you look at a series and it's getting smaller and smaller and smaller each term, you would think that it would eventually converge to something. This one is getting smaller and smaller and smaller, yet it is a divergent series. So just don't fall into the trap because each term is getting smaller that it converges. It may not. This one is definitely getting smaller. It is divergent. So keep that in your back pocket, that the harmonic series diverges. So, all right, let's look at, now I'm ready for the next test because you can see there's a link between series and integrals. And here is that link right here. So let me show you the next test. Listen to some inspirational music.
I'm having flashbacks to like the spring,
Christmas.
What's it called? Yeah. Yeah, but there's like a spring one too. What's it called?
This is like my favorite thing at Christmas.
That song?
Yeah.
Yeah,
Don't
me
we sing it at
too.
the spring? Did we sing it at the spring one?
It was sung at the winter concert, the Christmas concert. By the entire school. All
Alright, the next test. Alright, I'm ready to retitle the area of notes. It's called the integral test.
Oh, we're actually doing calculus now?
Yeah, we are. We're back to calculus. We did calculus a minute ago. You were helping me do it. You were doing an improper integral. I know.
Again.
Yeah. Alright.
I did forget, so don't feel too bad.
Alright, you can see from what my discussion just was, there's a link between the integral and series. So the integral test goes like this. Write it as I do. If f is continuous, a function is continuous, positive, and decreasing. So like I said, these tests are kind of very narrow. They only apply to certain cases. That's why we need a whole bunch of them, so we can test everything. If f is continuous, positive, decreasing for x greater than 1, greater than or equal to 1, and a sub b, we have a sequence, a sub n, equals, the nth term of a sequence equals f of n, then the summation, the sequence, the series from that sequence, a sub n, the summation as n goes from 1 to infinity of a sub n, and the integral of f of x dx, either both converge or both diverge. Alright, this is one of the times where I chose to give you the theory first. So you probably understand a little bit from what we just did, but it's going to become quite clear as we do our examples. I probably do like 1, 2, 3 examples and make a conclusion, and you'll be off to your homework races. So, the first example, will you catch it over here in the corner, Johnny? Right over here.
Yep.
Okay. Let's see if we can apply this test to n equals 1 to infinity, the summation of 1 over n squared plus 1. And to do that, I need to know if it meets the qualifications, which are continuous, positive, and decreasing. So you have to be the continuous, positive, decreasing police before you can even apply this test. So we can call it the CPD test. Cops, what's P? Police.
Police department.
And detectives. I don't know, or all right. So the CPT test has to be conducted first. So how do we know if that is positive, decreasing, and continuous? Well, continuous means you don't pick up your pen or chalk the whole time you're drawing this curve. So it does no jumps, holes, or asymptotes. So let's the really true way to find out if it's decreasing is if its first derivative is negative always for n greater than 1, or x greater than 1. Let's just look at it at the calculator because I want to spend more time on the series and less time on the actual prerequisites. So put in 1 over n. I can see it's always positive for whatever value I put in for n. The function is positive. Excuse me. 1 over x squared plus 1, does it look like it is, after x equals 1, is it decreasing?
Yes.
It won't graph mine.
All right, what kind of window do you have?
Hundreds.
Pardon?
Yeah.
You don't need 100. Just do zoom standard and it'll give you a pretty normal window. All right. Yours, Johnny, it looks like it meets the police, cops, detective. All right, positive, continuous, and decreasing. So we have to do the CPD test on every single one first. All right, so it meets the requirement. So now we're going to take the summation and look at it as a function instead of an nth term. So we do that by just calling it. They're not equal, but we know if this converges or diverges, so does this. So we're going to call it this, from 1 to infinity of 1 over x squared plus 1 dx. Now we're in familiar territory. We spent all that chapter 8, which was eternal, figuring out how to integrate the world. So here we are integrating. Again, it's improper, so I showed you how to do one before. So how do we do that with the b's and so forth? Brendan, since your name starts with B, what do we do?
You put b and limit as b goes to infinity.
And where does that show up over here?
1 to b.
Right, 1 to B. And Gianni, what is the integral? Do you recognize it? It's pretty much by recognition. You recognize that?
It looks like it would be like an arc something.
Yeah, an arctan. That's an arctan. So the arctan, so we still have the limit going. The limit as n approaches infinity of arctan of x from 1 to b. We're plugging in. So we end up with arctan of b minus arctan of 1. So Morgan, we still have our arctan graph up there. What's happening in infinity for arctan?
Going to pi over 2.
What about arctan of 1, Morgan? Do you recall what value on your unit circle had a tangent of 1? That's where the sine and the cosine, the sine divided by cosine had to be the same.
Is it 1?
It's not 1. At 1,
Wait, I gotta get out my unit.
Couldn't you just look at the graph too?
the graph of 1 over x squared plus 1? No, which graph?
The graph of arctan?
Yeah,
It's pi
arctan of 1. Yeah, but
Over
where's
4.
1
Pi over
on
4.
here?
That's true.
over 4.
Pi over 4, it is. Right, because at that point, sine is what? Square root of 2 over 2, and cosine is square root of 2 over 2. So when you divide the 2, you do get 1. So it is pi over 4. So we get pi over 2 minus pi over 4, which is pi over 4. So this integral converged. It went to a number. Does that mean the series goes to pi over 4? It doesn't. But it means it does converge. So this, we know that this series Therefore, here's the symbol for therefore, it's a mathematical symbol, the 3 dots. Therefore, n equals 1 to infinity of n squared plus 1 also converges. So it's a pretty strong test for those functions that meet the CPD requirements. Alright,
But it doesn't converge to pi over 4.
right, it does not.
Oh.
It's just,
Well, we have to figure out what it
you're
converges
sorely
to.
tempted to say it will, but it doesn't.
Okay.
No, at this point, I'm just asking you converge or diverge.
It's
alright.
been 10 minutes.
Alright, down we go again.